Um, the first thing I want to make sure is that you're making some progress deciding what you're going to be presenting on this term. I'm happy to talk with anybody who wants to do something related to material selection, processing, the kind of things we've talked about with any material really or any process. There's a lot of flexibility, as you know, and I think the most important thing is to get started early. And it doesn't hurt sometimes to just talk about it a little bit, what you're thinking. I've seen some people kind of rework something that they've done before. That's perfectly fine. If you want to try something new, I think it's a great opportunity. There's definitely a lot of support we can provide, just kind of guiding you towards, this may be a little too complicated. You may look a little bit into this. There's a great variety when we ask you guys to decide what you want to work on. I find it always interesting. Some people would want to focus on the process. Some people may want to focus on why this thing failed, why, it's just very, very variable. And it's perfectly fine. What Professor Eager has been a big promoter is trying to avoid you being too broad, because that doesn't really get you to apply, some of the skill of engineering. If you just try to give us a real overview, people can design things all sorts of ways. That's a little bit too general. So it's often very nice if you put into a certain context and then you expand more in depth into what you were interested in and what you researched. Welding is a good example, although I understand that we went through it pretty quickly. We're going to do just a little bit more today. Last time, I think I've given you a number of examples. It was a little busy, but hopefully you got some good idea of how the process works and what are some of the important aspects of it. So we'll just summarize that. We're going to go over different common welding processes and why we have so many of them. So I'll give an example of each as we move forward. And after that, we're going to start talking about surface modifications. There are a lot of them. So of course, I won't cover everything, but I'll cover things that are used widely and yet not discussed, necessarily in other classes. So I mentioned that the diffusion welding here is not necessarily very homogeneous. You have a starting point and you have a finishing point. So here, when the last bead solidify, this region tends to have even more residual stresses. So there will be some very advanced specification, including when we were looking at the radio telescope, that they'll require you to terminate the weld outside the joint and then grind off that portion. So it really depends kind of the quality standard that you want to put forward. We mentioned that in this case, because they were not able to completely clean the steel, they wanted to use a flux that was essentially going to completely extract not just the oxygen, but any other impurity in the metal. So other than it's a little bit more messy, creates more fume, and it requires cleaning, there's nothing wrong with the stick welding, is pretty much the bottom line we discuss in terms of quality. And it's still used frequently for high-strength steel. When we talked about higher strength material, that was the example of the mooring chain where they were doing a big flash weld. And then turns out they went through the entire heat treatment for quenching and tempering of the chain, and they realized they had a defect, and they did the local repair welding. And I said, well, they should have reheat treated because they created that martensite in the joint, and they just couldn't move forward with it. So the alternative, which I haven't mentioned a whole lot, but I'll bring it up here, is if you have the ability to preheat the base metal. In this case, if the entire link is, there are different specifications. Let's say we go for 200 degrees centigrade or 300 degrees centigrade, then we're able to reduce the cooling rate, so we reduce the risk of forming the martensite in the heat affected zone. It is done, and another possibility is what we call a post-weld heat treatment, and that's not a complete heat treatment. All you do is you reheat to temper the martensite. So you don't have to quench and do all of this. You just reheat it up to approximately 600 degrees centigrade. It's not too hard to do with torches for a few hours, and then you let it cool, and you know that you essentially got rid of this high hardness zones just next to the welded beads. So there's essentially a lot of ways to avoid having this type of cracking here that started just because it was as welded on fairly high strength material. We talked quite a bit in welding that what we're trying to do is reduce costs. So this is a sequence for forming tubes that involve essentially starting with a flat sheet that gradually gets rolled into a round shape, then it gets welded, and you can have all sorts of other ways. The sum of the process will have a post-weld heat treatment there just included in that loop. It's a very large facility, but it doesn't require you to deform the steel with mandrels or try to do it with extrusion or drawing it. So it requires much less energy to form a pipe this way than it would just by drawing and extrusion and forming. So the main consequence here is you are left with that welded seam that's essentially in the hoop stress. It's in the circumferential stress direction that it's likely to open up. So when I was introducing the technology I've been working on for evaluating existing pipelines, that is an area of high interest because this way of the way you can form these welded seams just varied from the 40s to the 50s to the 60s to the 70s, and they just keep improving how you can make a good quality. Essentially, because it's relatively low strength steel, it's good to have a very localized heating, so your cooling is high and you avoid forming zones that are too soft. If we were to look, so this is not typically done and left as is on high strength steel, although, no, I take this back. Even with P110, like very high strength steel, you can still have these welded seams, but you do the weld treatment after it's welded. There's no way out of it. So you start with a flat sheet, and in a relatively soft condition, you form it, you put the weld, and then you do the entire heat treatment. So again, we'll go over the welding requirement and talk about different welding processes. So AWS D1.1, I posted on Stellar this morning a copy of it that's public because it's not the latest. It doesn't change a whole lot. If you scroll through it, it's 500 pages, but it's really an encyclopedia of welding. If you get familiar, even just with the general organization of the code, it really helps you a lot. They have a lot of details for all sorts of very complex geometries. They'll tell you exactly what to do and how to design. This is the table that I've talked about, this kind of table that shows you how your strength decreases depending on the type of joint. We didn't look at it for tube, but this is the case for tubes, whether you use essentially a gusset plate or you don't. Let's go to the beginning of this, see if I can put that in there. Say around page 6. So the way it's organized, it's got 6 different sections. The general requirement essentially talks about, as the designer, what you have to include on the drawings. It specifically says. And then it goes over that this is not a law. So somebody needs to ask you to follow the code before you have to do it. It talks about essentially how to design the connection, and eventually what becomes not so important for us, but it's good to know that it's in there. It has all the welder qualification. It tells you the requirements during fabrication, and probably as somebody that may ask for welding to be done, the inspection section, I don't know why it's not in order here. The inspection section, section 6 here, all sorts of basic requirements from the code is just a visual inspection. So everything else that you can require to know that you have full fusion, that you didn't create a crack when you welded, becomes all these non-destructive technique, and there are a lot of them, but they are supplements to the basic requirements. So they'll go in all the details about what is an inspector, who can do it, who cannot be it. And there's also a lot of appendices that provide a lot of extra information. So for anybody involved in welding, it's a good starting point. I think I had to spend 2 or 3 days learning it when I started working for a consulting company, and it was probably my best time spent, just because it forced me to think the way that we have to think if we're going to use welding in a critical application. Okay. So again, these are the sections of the code. The most important part, I think, is in design. It goes really over how you reduce the stress as opposed to the base metal. So if you're working on a race car or any building is not really exciting, but say you're working on a section of a spacecraft, it could very well be that you have less of a factor of safety, but overall, but you still want to make a big difference between something that's been welded and something that has not been welded, especially if it's subjected to cyclic loads. So the main trouble with the welds in service is because of all the residual stresses, the hard zone. It's in the long-term behavior. If we talked about this on steel, that it does have the ductility. It's not going to snap when you try to bend it. So you do the weld, you can hammer it, you can probably, a lot of times in just basic fabrication, they will do straightening. So they welded everything and they'll bend it until it's straight when it's fully fabricated. And just that by itself is not a problem if you do it once. But if you start going through a local bending back and forth over time, that's the fatigue. And if you have these residual stresses and you have a heat affected zone that's too hard, that's what both leads to fatigue or stress cracking, like we've seen in the chain example. The chain really didn't have significant cyclic load. It was so deep that any kind of storm wouldn't change significantly the load. It's really just time on the load that created the crack and let it grow. So it's a different way of failure, essentially. I mentioned mostly about AWS, and that's what I gave you guys on the Stellar site, but ASME has a lot of welding specification as well, and API has its own body of literature. What is unique with AWS is how step by step the overall volume is in going from all the way from the design to the inspection of the weld. That's, I think, pretty unique, and it's referred to sometimes even if it's not steel. So they'll say, well, do the qualification, do the inspection this way. They just change the criteria if it's another material. So we went through this at length. I'm not going to go too much more details, just to say that electrode, if we're using just conventional welding, has the filler metal on the inside, and it has the shielding, which becomes the the slag on the outside. It creates for the two faces. Depending on the polarity, you can heat more the base metal, or you heat more the part that you're welding to. So it's really advantageous. It's the filler. So you can have more deposition faster when you're in the reverse polarity, but you get less fusion of the base metal. Okay, now a lot of times if it's a series of fabrication, you'll see a spool on the machine, and what it means is it's a semi-automated process, and there are a number of them. So the spool allows you to continue welding as long as you want. And you can vary the speed more easily. You can control the amount of metal that you're putting at a certain rate. The most common way these days to do the semi-automated welding is the MIG. So gas metal arc welding. The inert gas here essentially is just preventing the oxidation of the metal. So you see it coming on the very outside here. So everything that's very hot is protected, but it's not really reducing, or it's not cleaning up the impurities, so you need your material to be clean in the first place. It's great for aluminum. For example, it's used a lot for stainless steel, because stainless steel, if you start putting a flux by itself, you introduce carbon, which contaminates for your corrosion resistance. So this is a really good way to weld stainless steel in large quantity. The same machine, you just change the wire and the parameters, and you can do all types of materials. So it's a great kind of small fabrication technology. It's used in automotive because you can have it in a mode where you really don't fuse much the base metal. If you work it in reverse polarity, you can weld very thin metal for a seam weld. So the way the automotive people do a lot of their welding is they'll have one side, they'll have the other side, and it's very thin, so there is no prep, and they put a bead on it, and it just fuses everything like this. So that's unique to dealing with sheets as opposed to very thick sections. That's unique to MIG. The other processes, this one here, the flux core, is actually the opposite, because it works in negative polarity. It provides a lot more heat to the base metal. So this type of process here it will look a little bit like a stick electrode. That's what the wire looks like, because they have it two ways, but in a basic way, you have the metal on the inside, and you do have a flux. So you're able to clean. You can work on different materials that may have had some paint, some rust. You clean it up, and then you go and do the welding. They supplemented sometime with gas as well. So then, it's even better, but it's essentially a high penetration process. So if this is the case where we'll just have, a big prep on one side, and we're trying to fill it up quickly and have a lot of fusion in our base metal here, and then finish it up. It's gradually becoming, overcoming the stick welding process, although it requires more qualification because it's still relatively new by welding standards. Sometimes things don't change very fast. So I'm putting just the first bead here, and then to completely fill the joint, there's another bead, and there's another bead. So whenever you have something that's more than about 6 millimeters, you end up having to do multiple passes. And you want to use the semi-automated processes if you can, because it allows you to work faster when you have a lot of material to build.
It should be like a V, both sides.
No, so I know what you're saying. So that this is the bevel preparation, and you're referring to a V groove like this. And there's another variation where you don't have to go all the way to the depth. The only one trouble here is you have actually more material to fill, because here you just have an opening of 45 degrees, and here you have 30 degrees on each side, so it's 60 degrees. So this detail, it looks great, but it requires you to do more welding, and therefore it's not very common. You know, you can do it, it looks great, it looks symmetrical, but it requires more filler metal, so that means more distortion in the end. Another process that is used for heavier, even heavier, so we have it in the right order. Say we have plates that are 2-inch, 3-inch thick for beams on bridges or large structures, nuclear facilities. You have to think about a way where you can do all that welding at once if you can, just because of efficiency. So the submerged arc welding, essentially you use sand, not just for, it's not just for shielding the metal that is fused, but it's also to reduce your cooling rate. It's essentially putting a blanket on what you're welding. Probably the most common example is when you try to fabricate beams or large connections. A little bit like this detail, but let's say I'm trying to build something that is just really large to another component that's fairly large. That would be an example. Say this is, I don't know, we'll say 70 millimeter here, going into something even bigger. If I can do this in 3 passes, I will. So with a flux core, you can go to a 1-inch size weld or more, so 25 millimeter at the time, as opposed to here with a semi-automated process, you're limited to 4, 5, 6 millimeter size welds. So it really depends what you're building. The biggest trouble as you start growing to these sections is everything is larger, and even if you reduce your cooling rate, you have a lot of distortion. And that's one reason why on something like this, it is much preferable to weld it from both sides to reduce that distortion. You have a little bit pulling one way, you pull the other way, you pull the other way, and then hopefully you end up straight. And they do that essentially by experience. They'll do 1 pass one side, 2 passes the other, and then things don't move as much anymore. So it's all about fabrication cost when we're talking about welding. We've seen a lot of these processes, so I thought it's great to finish up this section on metal forming and processing by talking about welding, because it includes everything. And I hope you realize in terms of design that essentially not only saying the type of filler metal, but the process becomes important, and mostly the inspection requirements are very important to include if it's needed. A lot of times you can avoid a lot of trouble if you really go to somebody who's done the same thing already. So when we were talking about the distortion, for example, it's so common that they will a lot of times have a calibration step. They clamp everything on a large structure. For example, let's think of this. There's a big industry for making locks. So if you have canals built everywhere, different countries, and then you have to put essentially barrier to the water. We'll talk if in a canal you have, I don't know, 100 meters across here to cover. That's very typical. And then you have maybe, I don't know, say your elevation here is 15 meters. We'll just take one example. You want to close all that up at once, up and down. You need something that is not super heavy because all the loading mechanism to get it up and down is not going to work. You need this to seal, right? So whether it's loaded or unloaded, you can't have it deflect so much that you're not going to seal against the interface. So the way a lot of these are built is they'll have a lot of trusses going across from one side to the other. So if we look at this from the top, we'll see the equivalent of our joist that we were looking at for any roof application. So say we have a joist here. It gets loaded in tension, and all of these components just have a lot of welds into it. But when they come to the main panel, it has to be very, very precise. So they have this special way where the main element here, if you want a very straight final product, is for each assembly, each joist to be very straight. So they essentially have to build up these rigs where they hold each side here very, very carefully, and they have their welding sequence always the same. So they put a camber on it on the first place. They do their welding. When they release it, it goes straight. Now, if they change anything in the process, the sequence or the amount of welding, it's not going to work. So the reason they do this is it's not cost efficient to try to take these assemblies and straighten them. There's going to be other issues that are going to come up. And sometimes even in the contract requirement, they're not allowed to do it because you can introduce defects when you're doing that. So it's a very delicate balance of making these precisely enough, making sure they're straight on the side that you put the panel. So this is not, if this is just hanging, you don't mind, but you need one face to be really straight. And it's a very large issue in terms of manufacturing. Now, of course, they add a little bit of reinforcement the other way. There's just a lot of structure here to be, relatively lightweight and yet stiff. Because under the deflection from the water, you don't want this to deflect too much. So they have to apply all of the design, specification, inspection, but they have their own ways and methods to be able to make a straight final product. So the other example, perhaps that's completely different to this, is for the radio telescopes we were talking about. How big it was, and I said, we need a special gearing system to control all this. So when they have to design the machinery for gears, a lot of times they'll do the welding. They put the entire assembly for a heat treatment to take all the residual stresses away. That's a good way to do it if you can afford it. And then they do the final machining. The reason is in the production process, there's going to be some variation. So if you're trying, say I have a big gearbox and I need a very high precision in how I'm going to have one side hole here and another side hole on the other surface here, for example. So these needs to meet very precisely. And this is, I don't know, this is maybe 4 meters in size. So I need a lot of this to come together as a welded structure, and then I come and do the final machining of the components in place. But if I didn't do my post-weld heat treatment, my stress relief treatment, then as I machine out some of the details, I can have some more distortion going on. So that's one of the reasons for doing the stress relief. So when you come back and machine, there's no reason for the material. There's no spring loads inside the wall of the structure, so there's no reason for it to move again. So just completely different. Any questions on welding? Because I'm about to move on to something else. It's used a lot.
This AWS code is not legally binding. It's optional.
So it will be required by some building codes, for example. But it's not, if you're doing a project that is not into the building regulation, no, not required. If you're doing a greenhouse, apparently it's not required, because it's a product as opposed to a real building. Yes?
What about like TIG welding versus MIG welding?
Yes. Okay. Yeah, I said I was going to go through this. Thank you. The main advantage of TIG is that you have a permanent electrode in addition to your filler metal. It's very advantageous for aluminum, for example, because it's very hard to control the arc if you're trying to do something very precise. So people tend to think, oh, you know, it sounds research oriented. You know, I'm going to use a tungsten electrode. It doesn't seem like I'm doing something productive. But more and more of the aluminum welding includes the TIG electrode, because you have you can do just the inner gas with the tungsten electrode, and that's autonomous welding, and then you just essentially bridge the two pieces of metal together without adding any filler. But the most common now is you also have the filler metal, and the main advantage is if you need a good control. So if you're welding thin sheets of aluminum, for example, on roofs, there's the new convention center in South Boston that has about 5 miles of TIG welds. That was on stainless steel, it wasn't aluminum, for the reason that it was so thin and it was required to seal. So you need a good control over your process. So that the only downside is you really saw all the guys just sitting down, and because it is a slower process, even if it's optimized. So it's almost like a paint job. The guy goes and, you know, about that speed that if you're going to do 5 miles. Yes?
Do you see a lot of processes that are automated TIG welding? Like, do you have like a second robot feeding in the filler metal and one robot that controls the arc?
So that's a little bit what the TIG will do for you, yes. So but it's not really automated. If you're talking about industrial processes, it's not common. No, there may be. That's, you know, an area for future welding development. There's a lot of welding processes we haven't talked about. Just friction welding, although you've seen it with the pipes when we bring them together, and it's the heat that and the deformation that gets them to weld. So this example of very controlling you have it in torch brazing to some extent, but then you don't have to really fuse. So you put the heat and then you bring in the filler metal. That's a little bit what happens. It hasn't really come common for any of the stuff I've seen. Yeah. All right, we'll move on to something that is, I guess, a derivative. I call it a derivative of welding. It's a series of different deposition processes. I can't go to, you know, the details of every single one of them, but I'll just say essentially thermal spray processes that essentially allow you to take wires or particles, powders, and apply them to a surface with heat and velocity. This schematic just tells you a little bit that there's a lot of variation in terms of the temperature that you can process at and the velocity. It's used across a lot of industries. If you need a wear resistance on the surface, for example, you can put that. If you need a corrosion resistance, you can add that. For aircraft engines, if you need a very high temperature oxidation resistance, you use that. So it's used for a variety of industries with the main goal to be, okay, I have a material, and now I'm going to add gradually more to it. The thermal spray community has been trying to move into additive manufacturing, so it made freeform for a long time before we started using the term. But one trouble that you can probably anticipate here is there's a lot of heat each time that cools fast on the surface, so you're building up residual stresses. So most of these processors will be limited in the thickness that you can fabricate. Otherwise, we'll just use them to make full assemblies because they're very efficient. But there is that limitation in terms of the amount of residual stresses. So every half a millimeter, you have to do a stress relief if you want to continue. That just doesn't seem really practical. It's been around, if you look at the history, for 100 years. What exactly happens, even if, whether you use a wire or not, you end up with particles that are heated and they come to your cold surface, and some of them, depending on the environment, may oxidize. You're going to have some porosity. You may not adhere super well to your surface because you don't melt that surface. You really just come with particle down to it. So that's actually the preparation of the surface before you do this thermal spray is one of the most important steps. You need this to be very rough. They'll do a grid blasting normally, so because it's mechanical interlocking that's holding your coating on the surface. Why would we do this? There's a lot of different applications. And say you don't, in the spectrum here, say you use what they call a cold spray. So the cold spray, you don't melt the particle that's coming on the surface. It becomes hot, but it's not melted, and it's in a reducing atmosphere. So they've been doing this for increasing electrical resistance. So you can add copper to the surface if you need to functionalize the part for electrical conductivity. You have copper, you have aluminum that can come and be almost unaffected. It's not really a bulk material, but it has good level of purity. The other end of the spectrum is if you're going to plasma heat ceramic particles and put them on that same surface. You will try to think, oh, how am I going to put the ceramic on a turbine engine, a super alloy? And this allows you to do it by that mechanical interlocking. So each particle hits the surface and gets adhered between the pores. One thing that happens with a lot with the ceramics is after they come to the surface and they cool down, they crack. But it's what's very interesting here is these cracks actually help to allow for thermal expansion. So you'll think that you'll try to make this process with as fewer cracks as possible, but you don't. You want some cracks to allow for difference in expansion. For engines, the way it ends up working is, say I have my super alloy. Good. No, here. So say I have a super alloy here. What I can do, so I add a bond layer that provides me my oxidation resistant. And then I'm going to have something that is more porous on top. That's essentially an oxide forms in different ways. You can do it by chemical vapor deposition. You can do it by thermal spray. This one essentially is just a thermal barrier. It doesn't really protect against chemical attack or the gas itself, but it reduces by far the temperature that this layer gets to. So you have a temperature gradient between the surface going through a structure that will look like this, and if it has cracks in two directions, even better, because I'm even reducing more my thermal transfer through the material. So it has grown into a fairly large industry. and it's optimized to a point where you can ask for just about anything you want in terms of thicknesses and in terms of durability versus the barrier properties. Another variation, probably we'll call it a third variation of this, is in between, where you're not looking for a new function, you're not looking for a thermal barrier, you're looking for wear resistance. I'm showing here just because I thought it was interesting when I learned about it. I worked for Schlumberger for a while, and they had all sorts of ways to do directional drilling. But there's one common pattern here. You look at all these red points, is you're going to be touching the formation all the time. So that drilling equipment needs to fit into the hole. So when you start, it's very easy. You got a pretty sizable, a 2-foot hole, and then you go down at the end, you have about maybe 4 inches, and you still need to fit all that equipment in. So the characteristics of any drive system, this is just a pad that gets actuated for a different height. So as the drill bit rotates, you just actuate those pads to change the orientation. So it's exposed to the formation constantly as you drill, and you won't mind the weight, you won't mind necessarily the long-term corrosion resistance. So you want to avoid stress cracking or something that will cause it to break. But if there's a little rust here on these parts, that is not a concern for anybody. So they end up using a lot of composite structure. One that is very common here is you have tungsten carbide inserts. So say I put them on the surface here. These are very, very hard particle, but they are brittle. So say the pad finishes here and it's oriented this way. I have essentially small cylinders that I put on the surface of the pad, but I need to assume that at one point one of them is going to break. And I don't want this failure to cause the entire pad to fail right away. So that's why you end up having a lot of them, and you can have them of different sizes too. So say, and you put your front row with small ones, of course. So if this one fails, you don't want that to propagate into the next layer. So they'll have these tungsten carbide inserts, and then they'll thermal spray a good wear-resistant material in between the inserts. So you have a composite at 2 levels. You have the macro composite, where you have these very hard wear-resistant surfaces, and then what you deposit is a cemented tungsten carbide, or something that essentially has some small particle of carbides, but in a ductile matrix. And thermal spray is a good and efficient way to do it. These parts need to last sometimes, say, 400 hours. And then but if they have to pull the entire equipment because they've lost the drive system, that is not good. So there's essentially a minimum wear resistance it needs to have to survive one cycle, one round of drilling. The biggest issue, other than wear, that I've seen with this type of equipment is the erosion. Because you're coming down with the drilling mud that has some small particle in it, and you essentially distribute that mud around the tool to bring back up all the, so sometimes the mud comes here, but there'll be a little bit coming out of here as well, just to provide lubrication. But all the internal components, wherever you have essentially a nozzle that provides the fluid, it gets abraded and eroded, so they'll have to put inserts at all those locations as well, and essentially install them in a matrix. So you say I have an access hole here, that's good. So it's an access hole in a very brittle material, and then I'll surround it with all my my thermal spray coating, and I have a structure. I'm ready to go and do some serious drilling. Anything about drilling? It's very interesting. The mud always gets circulated, so it comes from the inside of the tool all the way down and then back up from the outside. So you can take that. The biggest problem is on the surface, you have a fluid coming down and you have a fluid coming up into the hole. So in trying to seal that structure is, why blowout preventers are a great technology and always need improvements. Now let's go to something much less advanced in the sense of level of technology, but used a lot more broadly in terms of volume. So if we made a complex structure, if you take a frame for the radio telescope, for example, I just made it, it's all great. I made the precision and everything. Now I have to decide how I'm going to protect it so it lasts 20, 30, 40, 50 years. Turns out for steel that putting a zinc coating on it is a very, very useful way, for the reason that if I scratch it locally after it's been dipped, it's self-protecting, and we'll go over that tomorrow. Now, when it gets protected, it doesn't mean you won't see a stain or rust on it. It just means you won't really lose thickness. So this is for an application where it's okay if it doesn't look pristine. So we don't have galvanized cars for more than one reason. I mean, it's a little rough surface, so it's not as shiny, it's not as clean. Maybe one day, if we have Priuses and all these, hybrid cars, that may be a next step up. You don't have to worry about having the coatings to be environmental friendly. You just essentially put zinc. So it's done with cars, just so we all know. The sheet metal of cars for the past 10 years or so, they go through a sequence where they get cleaned. Which way are we going here? So they get cleaned in the process, they get dipped, and then they go through a heat treatment. What the heat treatment after the dipping does is it roughens the surface. So you have a zinc coating, but putting the final coating, the paint on the zinc doesn't give you a good adhesion. So what the car industry has been doing is they go through a heat treatment that causes some oxidation of the zinc layer, and then it's rough enough to cause the adhesion of the paint on it. So you essentially make a corrosion protection. You consume a good fraction of it just to be able to put the final coating on. You can see an implication. I take it nobody likes to have a brand new car and then you have you get hit and you get it repaired, and it never lasts as long after it's repaired, especially these days. And one of the reasons is they won't put the zinc coating when they do the repair. So that area doesn't have the protection that everything else in the car does. You could do it with the thermal spray process that we just talked about. You can easily sandblast the surface and put the zinc coating on, and probably we should all get the insurance companies to cover it, and that would be a big improvement in terms of the longevity of cars that were repaired. So that's all I had for today. And again, if you want to talk about your project, I'm happy to do so. Tomorrow we'll go over all sorts of ways to prevent corrosion, how it works, and how to prevent it.